I'm very excited to talk here today, but kind of wish it was under better circumstances. Jan, in case you're listening on the live stream, we really hope you will come and visit us as soon as things calm down. So what I'm going to talk to you about today a little is our ideas on origins of life and how catalysis is important in those ideas. ELSI is a very interesting and very excited place to work at times. It's maybe one of the only institutions in the world whose mission is to understand how planets make life. So I myself have been doing prebiotic chemistry and the origin of life for a while, and it's been quite a humbling experience because it's just as soon as you learn something, you understand how much you don't know. It's origins. Life is an interesting subject to study. For once, we don't have a good definition of life. So this is maybe the closest one. It's a NASA working definition. But to me, it seems like a little bit self-referential. So we're thinking this describes the life as we know it, but not generally. But we can't really do any better because so far we only have one example of life, and we don't have any points to compare it to. What do we do? And it's a large field. A lot of people work in the origins. And in broadest sense, people work and take two different approaches. Some is more Earth biology centric. And this one would involve prebiotic synthesis of biological compounds, setting biological processes in some prebiotic setting. Top-down approach, stripping down biological instructions to their ancestral state. And a different approach would be a little open-ended. Let's create prebiotic chemistry setting and see what it does. And there are problems with both approaches, and I like to explain it usually with my TV paradox. So we have one example of life, and it's very evolved, and it's sort of like super-duper advanced, state-of-the-art TV set. And if I take some of you and give you this TV set and tell you, figure out where TV technology comes from, I don't think you would ever be able to get to cathode ray TV. Well, that's kind of the problem of origin. However, if you start bottom up and try to be open-ended, it's really unclear where you should start. But we do both. So here at ELSI, we're thinking about origin of life, and we call our approach messy chemistry. So basically what messy chemistry is system-level approach, system-level study of prebiotic chemistry. And the only reason we don't call it systems chemistry because it just means different things to different people. It's usually a technique that involves very small, defined chemical system. So in our mind, prebiotic chemical system, messy system, is large, intractable, dynamic. And so what we think it does, so there could be some sloppy biological processes happening inside messy prebiotic system, but they're not as efficient and it's not as obvious. So if another definition of life, if you will. So how do we think what separates life network or metabolic networks or chemistry of life from any dynamic chemical system? It's the level of order that you would see there. So here we're looking at metabolic pathways, and this is a very, very complex system, maybe not unlike Tokyo metro system. But if you're thinking about it, it's very complex, it's hard to figure out, but trains come at a given time and they stop and they're being controlled, and pretty much the same thing enzymes do in our bodies and in any living organism. So what is messy chemistry, prebiotic chemistry? I'm thinking it's a much larger subset of any chemical reactions happening without any methods, very efficient methods of control. And so what we need to understand in our process of chemical evolution, how do we increase order in those systems while maintaining their complexity? And here in this talk, I'm going to cover a couple of topics we're thinking about here. One of which is based on our plausible prebiotic system. We're looking at some biomimetic system. I'm going to talk about protoenzyme. And I'm going to talk a little bit about some of our open-ended system. We'll talk about autocatalysis and molecular memory. So we talked a little bit about TAR yesterday. So if you're not familiar, it's completely, absolutely true. If you create a prebiotic system, complex system, what you're going to end up is like this Tarry complex mixture. And this is true for well-studied hydrogen cyanide polymers. So a lot of us have heard that Miller-Urey experiment produces amino acid, but what we don't know that the major component of those mixtures is actually this black Tarry polymer. And something that this brownish color of Titan atmosphere or Titan surface is also due to Tarry polymers. What do we do with this? And can we have them be functional in some ways? And the answer is yes. And we're probably not the first one to ask this question. And I want to bring this work by Sidney Fox. So it's happened in the late 50s, early 60s. So what Sidney Fox did is just he heated mixture of amino acids to 200 degrees or higher. And when he looked at the resulting kind of messy polymer under microscope, he saw those microspheres, what we call. And so he went ahead and he showed that those microspheres have some catalytic activity. And it's usually with many things in life, there is the good, the bad, and the ugly about this system. Well, the good is, it's like, I think it was a very revolutionary idea and it did show some functional messy polymers. However, the bad was he somewhat oversold the idea. The catalytic activity those polymers shows was only marginal. And as the things progressed, he kind of started talking about lifelike behavior and consciousness of those microspheres, which really angered a lot of people. And I believe that's the reason why this work has never been followed up. Can we do better? And the answer is yes. So here at ELSI, we're kind of enamored with polyesters because it's a very convenient model system to work with. We're not saying that this is how life started. And the reason we like it, it's because polyesters, and I think structurally they're sort of similar to polypeptides. They have been proposed to be precursor to peptides. However, because of the negative energy of formation, we can make them in the lab very easily. We can very easily play with them. And what I was also talking about, I just got interested in prebiotic TAR ideas. So when we say word polymer, it's usually what pops up in the mind in those long linear chains. But especially in messy prebiotic TARs, that might not be the case. We probably more likely to get polymers that are branched, that are cross-linked, that we would polymer that are linear. Can we use that to our advantage? Of course we can, and we're not the first to do so. For example, branch polymers are a well-known, very interesting system used widely in the industry. Why so? Because hyperbranch polymers are those globular polymers with very abundant functional groups. With intramolecular cavity, they can absorb substrate. They are more soluble than their linear counterparts. And as such, they've been used in the industry as additives in different formulations like coatings. They've widely used as supramolecular encapsulation agents. And I don't know if they're already being used as drug delivery system, but there is a large amount of literature dealing with that. So can we turn them into protoenzymes? So let's think about it for a moment. If in a very simple way, how would you describe an enzyme? So enzyme is this globular polymer that consists of folded protein, sometimes RNA. And they know what actually does the catalytic chemistry within that enzyme is it's like catalytic core or active site, which is usually comprised of a mineral cluster or a small molecule or a cation. So, I mean, something like if you think about very structurally about how to approach to synthetic enzymes, it's been done in the industry, and it's been done by so-called dendrozymes. So what dendrozyme is let's say we take our catalytic core and we scaffold it with layers or generations of branch polymers, and voila, you ended up with globular polymer with an active site. And in some cases, those dendrozymes are almost as efficient as enzymes. Of course, this system is very engineered. So what do we do to translate it to prebiotic chemistry? We'll take cousins of dendrimers, hyperbranch polymers, which retain a lot of the same properties of dendrimer, however, in less controlled way. But those can be really prepared in one-pot synthesis on a prebiotically plausible way. So one thing that just occurred to us to try at first, well, can those polymers, because they're globular, they can modulate environment within them, can we harness that property to catalyze certain reaction? And in this case, we did this assay, Kemp elimination assay, that's just a very widely used reaction. Nothing prebiotically interesting about it, but a couple of things are. So it's very sensitive to medium and polarity. So it proceeds sluggishly in water, but if you put it into apolar solvents, the reaction starts proceeding very fast. Another thing, very nice thing, this reaction produces colored products. So it just very straightforwardly, one can follow it over in the UV vis detector. So what we thought about, let's force this reaction to happen inside hyperbranch polymer and see what happens. So reaction is base catalyzed. So we synthesized a few different hyperbranched polyesters. And here we took citric acid and glycerol and triethanolamine. And the reason being we wanted to have the base as an active site, and this is our amine, that's what it's doing. If you're looking at the mass spec over there, the system is truly, really messy. It's not very long. We're probably talking about like 8 mers or 9 mers. But we have many different molecular weights and many different architectures of the polymers. So glycerol and citric acid was our polar system, and we did a couple of less polar systems, which included adipic acid, glycerol, triethanolamine, methylsuccinic acid, glycerol, triethanolamine. And so this is what we did what happened when we tested Kemp elimination reaction. So when you take monomeric triethanolamine, the reaction has certain rate, and you see it there in red. With citric acid and glycerol, well, it works a little bit better, and it works 3 times as fast when we do it with apolar methylsuccinic acid glycerol polymer. And of course, we amplify the rate of the reaction by a factor of 3. There is nowhere near enzymes, but remember, enzymes, those are peptides with like hundreds of amino acids. Here we're talking 7 mers and 8 mers that are doing this reaction. And maybe, when you're talking about organizing a chemical network, like a little amplification is maybe that's all you need. So the next thing we thought, okay, Kemp elimination is nice, maybe let's do something more biologically relevant. And this is like a recurring theme in many origin of life research topic is the origin of metal sulfide enzymes, because they're considered by some to be most ancient ones. So metal sulfide clusters are found nowadays in enzymes like ferredoxin, hydrogenases, nitrogenases. So that's kind of the basis of iron-sulfur world theory. And they're also the basis of zinc world theory, which in this case drives metabolism by kind of photocatalytic catalysis of zinc sulfide particles. So what we decided to do, let's make a zinc sulfide protoenzymes. And why zinc sulfide? Well, first of all, we do have the zinc world hypothesis. And then again, zinc sulfide is a very well-studied system, so we have some basis to compare it to. So what we did here, we took a commercial hyperbranch polymers, and polyetylenamine here. We prepared a solution. It's very well soluble. We added zinc chloride solutions. Then we added sodium sulfide solution. And so what's happening there? So usually, obviously, when you prepare zinc sulfide, it create this white precipitate, but it never happened in the case of when we just had our polymer inside our system. So when we actually looked by DLS, it was, we thought seems like we're having some pretty small nanoparticles. And obviously, next things to do is to run a TEM. Now we're here, we're looking at fresh sample and samples that have been sitting out for about 2 weeks. When we do high magnification image, it doesn't render as well as I hoped. But we can see we will see a lot of those little round particles that are about 10 nanometers in diameter. And it looks like, if you just let it out sitting for 2 weeks, it's pretty stable. You can get some aggregation, but you still have a lot of small particles in that system. Well, commercial polymer, it's nice and well, but let's translate this system a little bit into a prebiotic world, and we do it usually with polyesters. And that's maybe I can foreshadow a little bit the next topic I'll cover. So we've spent a lot more time than I care to admit, figuring out this system. It turned out that we weren't able to form any nanoparticle-supported systems when we used polyesters. And why is that? So we bought actually very expensive dendrimers. These are polyester terminated in carboxylic acid and in OH groups. And in both cases, and we measure it with cobalt, once again, cobalt is more convenient system here, it has color. And we figure out that actually those divalent cations are not being absorbed almost at all by prepared polyesters. However, what was interesting when we actually went and prepared our citric acid and glycerol polymer in the presence of cobalt in this case, we saw that system can retain almost as much cation as does this commercial polyetylenamine. So just remember, think about that. The system remembers how it was synthesized. And it's probably the reason it's doing it is, in this particular case, citric acid is a fantastic chelator. So when you introduce the system, citric acid, divalent, you create a lot of chelates, and you're not, in essence, polymerizing citric acid anymore. You're polymerizing those chelates, so you're creating binding sites within your polymers already. That was kind of cool. But let us get back to our system. So how do we test catalytic capability of our nanoparticle-supported polymers? So we did it like many other people do in testing those systems. We did it with photodegradation of a dye. So over there I have a picture of a pink dye. And we subjected it to irradiation under UV, catalyzed or uncatalyzed, and followed the degradation. So over here, I don't know why it doesn't render that well. So when we do catalysis, let's say like UV irradiation without catalysis, or we introduce catalysis without UV, we don't see a lot of change in our system, and that we're looking in those top curves over there. So we get almost complete degradation in a little over 2 hours when we use our fresh zinc sulfide and PEI cycle, and it works almost the same whether we use zinc sulfide and polyesters that we synthesized. And it just so we lose some catalytic capability with an old sample, And we always would compare it to a commercial photosensitizer titanium oxide, like our system seems to be working better, but that's because the particle size. So great, so in this pilot study, in this first system, we created very messy zinc sulfide cluster or nanoparticle containing protoenzyme, and next things to do more interesting, more relevant to maybe biology and origin of life. But let me switch gears a little bit and tell you how we're thinking about constructing an evolvable system. Usually when we think about evolution, and that would be looking from a system that is capable of evolution, is selection. System needs to be able to replicate, and needs to be capable of heredity. So it needs to replicate its mistakes too. And so I think we talk a lot about, like Lauren Williams has spent about 2 months here, and we had a lot of conversations about chemical evolution, and nature evolution, what evolution. Don't have with the answer yet, but what we agreed so far, so what we need to be looking in the chemical evolution system, maybe not all of those traits. We only need to be looking at molecular memory. And what's molecular memory? Let me explain with an example. So one obvious example of system with molecular memory is a process of molecular imprinting. This is not prebiotic. This is how chemical sensors and sometimes chromatography columns are made. So take you have template, you self-assemble your template with functional monomers, you somehow invoke polymerization, now you have polymer matrix attached to a template, then you somehow remove a template, and you have a cavity that can maybe very specifically only bind that template. So imprinted material. And just we were thinking, so this paper appeared like 2 years ago already and still on archives, and it's written by Eric Drexler, who is one of the big figures in nanotechnology. And I think it seems like when, scientists about to retire, they start thinking about origin of life. It's just every scientist, Nick Hudd used to say every scientist is a closeted origins of life scientist. So he put forward his idea about molecular imprinting as a being important in abiogenesis. And in his way, well, let's think about this same diagram again. So you start out with some sort of peptide template with amino acids or small peptide monomers. So then you invoke wetting and drying cycles, which is popular nowadays in origins of life. You dry, you form polymer, you wet, you remove template. Oh, you have imprinted material or imprinted peptide. Well, this need to be tested yet because this is theoretical, but this is kind of our way of thinking about somewhat similar systems. So, for example, tar problem seems to be very well explained in my favorite system, Hyperbranch polymers. So when you're polymerizing Hyperbranch polymers, you take your multifunctional monomers, you polymerize them. They have like very nice properties we talked about, but it usually happened at very defined molecular weight. They suddenly solidify, change viscosity, crash out of solution, forming tar. And, so if you take, like ABX type monomer, for example, if you can make your Hyperbranch polymer from a single monomer, you avoid this problem. However, it's not realistic neither in prebiotic world, nor in the industry. So you have to opt out for different monomers. So in this case, you start playing different games trying to delay the onset of gelation and getting branch polymers. So what I was thinking about doing is let's synthesize our citric acid glycerol system subjected to wetting drying cycles, which are very prebiotically plausible. It could be day-night cycles, it could be seasonal cycles. And so what I was originally thinking, if nothing else, you would synthesize polymer during the dry phase, you hydrolyze them during the wet phase, and at very least, that way you can control the molecular weight of this polymer. And the result was kind of even better than we expected. Not only we were able to maintain our cycled polymers, no problem, ungelled for about 32 days. It's like also when we went ahead and analyzed the structure of that sample, we see that our system, cycled system, seems to be preferring branched polymers over linear and cross-link. Molecular imprinting, isn't that cool? And like last topic in last 4 minutes, I want to cover, it's like another way of organizing messy system, and it is something we're just actively working over here. We're thinking about autocatalysis in this messy system, and this is like really, I want to thank Nathaniel and Jim who are here. So thinking about replication, autocatalysis is a reaction where the product catalyzes its own production. That's the kind of very rarely found in chemistry. However, we're thinking autocatalytic set, which is autocatalytic network, where some product catalyzes the whole network or the whole cycle, are actually seem to be very commonly found in complex enough chemistries. And this is something that Nathaniel was pushing us. Let's create a complex chemical system. We will be sure to find any autocatalytic sets there. And so somewhat reluctantly, we humored Nathaniel, and we set up this experiment. And so what we're looking at here, so this is a combinatorial experiment with like different single carbon or 2 carbon sources, simple nitrogen sources, usually only like inorganic and 1 to 2 nitrogens. Sometimes we added cations, which included the cocktails of 7 transition metal cations. And another things we do, it's not usually done in any chemical experiment. We watch this system for about a year. So if you were to look for any chemical data, chances are you only would get data that is like, it was taken during first 48 hours of reaction. But here, this is what we're happening. I hope you can see. So we're watching, taking periodic picture, and you see especially with transition metal, colors change. Well, light goes out sometimes. But see, so what was kind of amazing is that there were a couple of samples here. There's another one that were sitting doing nothing for about 6 months, and all of a sudden, over a course of a week, they would turn black. Well, so what happens here? So what do we know so far? And analytics is really difficult with this system. We know that we need the salt cocktail to be able to show this behavior. We think so far, maybe or it might not be true, this color change is associated with aqueous hydrogen cyanide chemistry, probably. So I think the stronger, there's another experiment that we did. So we inoculated like fresh solutions with solution that turned black, and this transition to darker color happened much faster. And of course, it's all still in process. We don't know exactly what happened, but I think we have a very interesting indication of showing very simple autocatalytic process happen in a very simple chemical system. So I think I'm almost out of time, so I think I just end with a couple of concluding thoughts. So it's instructive and important in origin of life research to step away from tracing biology, because it's like not necessarily always useful, and in this way we might not maybe come to our origin of life, but we can discover some principle of universal life. So messy chemical systems it's where it's at. And even though bottleneck is analytical chemistry, we just should figure out how to work with it, shouldn't shy away, because this is where chemical evolution happens. And with that, I want to thank all those wonderful ELSI people, former ELSI people who just helped me with different aspects of this work, and those nice people who were kind enough to give us some money. And thank you for your attention.
Okay, thank you very much, Irena. Let's open up the floor to questions now.
Have you ever thought about mixing RNA with your polyesters?
Yes. So we will do it just like really, its inception. We're thinking about more cationic polyesters interacting with RNA, but yeah, this will be coming.
So we have a couple questions from Slido,
Ooh.
which were submitted by members of the audience. If you'd like to take a look at either of them and give your thoughts about whether assemblies, can you think of any examples of assemblies which inhibit functions, or how messy would you consider would be too messy, or is there a limit at all to such messiness?
Okay, let's say this messy is too messy. So I think it's all too messy in the eyes of the beholder. So I think it's like for a system to work, it probably doesn't care how messy it is, but it's, as an analytical chemist, it would be hard to really see what's going on there. I think that's my take. And need to think about, well, they just obviously are, just off the top of my head, I can think of in our system any example where we have inhibition. Yeah, but maybe during discussion, if something comes back to me. Ask me again.
Mm-hmm. Any more questions? Well, let's see. Let's have one of the early career researchers first.
Thank you so much for your talk. I was wondering if you were aware of dissipative adaptation, and if so, when you're picking biomolecules, if you would consider picking ones that as individuals are more dissipative or more stable under an energy input?
Not so far, right? I mean, it's a mixture of different things, but yeah, well, you just, when you're thinking about it, so dissipation, some of our linear polyesters are, let's say, they're less stable than our branch. So we have different stabilities over there. When we did it, whether we did dissipative analysis so far, no. But yeah, it's an important aspect of any system, dynamic system.
Thank you so much.
Oh, I'm just wondering the reason why your camp elimination is accelerated by some branched polymer. Mm-hmm. Maybe something to do with the topic in the previous speaker. He have shown the higher order oligomers resulted in the more oligomerized, the higher the activity became. Mm-hmm. Yeah, and something to do. And I'm just wondering, is there something to do with the excluded volume effect of the polymer chemistry? That may function to the effective increase in the concentration of the something. What do you think?
Well, yeah, definitely, yeah. That's one of the effects, but it's also polarity. But that's kind of why we try to synthesize few different. So I think with all our different hyperbranch polymers, the exclusion effect would be the same with all of our systems. But since within those three systems we looked at, there is also another effect that is different. So, yeah.
And we have time for one last quick question.
A quick one? Oh, that's not good. Well.
Oh, my God.
In a lot of fields, I think there's a dichotomy between people who build up from simple things to more complex things, mm-hmm. and then people who kind of arrive at a scene and they just see a huge mess, and then they're trying to distill order from chaos. And we have the same thing in planet science, which is fun. Mm-hmm. But I think this is a really important direction to follow, because I'm a messy geologist. So, but in any case, I'm wondering if other things come up in these systems, like chirality and stuff, and hyperbranch polyesters. I mean, do you get these kind of selection effects and whatnot in enantiomeric chemistry, things like that? Does it come up as much in polyester chemistry as it does in?
So I don't see, like in that particular, the way we set up our systems, Well, I mean, we were buying things from Sigma Aldrich, like citric acid, it's chiral. But the way we set up, I don't think there is kind of any mechanism for selection. But like to say that, we have never tested something like that.
Okay, so thank you very much, and let's thank the speaker once again.